Imagine trying to safely control a rushing river. If you need a gentle, precise trickle to water a single fragile plant, you can't just let the whole river wash over it. You need a way to slow that water down. The simplest plumbing solution is to just crimp the pipe, forcing the water to squeeze through a tiny restricted opening. In electronics, we do exactly the same thing to control the flow of electrical current. We use a component called a resistor. If you've ever opened up an old radio, you've probably seen them. They come in plenty of different shapes and colors, and they do a great job of resisting electrical flow. But there is a problem. While they work well for big appliances, these solid ceramic and carbon tubes are physically large. In the world of modern electronics, having components that take up too much space is a fatal flaw for design. To understand why, we have to leave the world of everyday objects and zoom down into the microscopic cities printed inside modern computer chips. Down at this scale, millions of components are packed into an area smaller than a fingernail. Space is the single most valuable resource there is. Trying to shrink a traditional resistor down to this tiny size creates major problems. They take up far too much of that precious space. It is incredibly difficult to print them accurately, and they actually drain the efficiency of the tiny amplifiers operating inside the chip. This creates a critical bottleneck for chip designers. Without physical resistors to safely restrict the flow of electricity, they need a new way to prevent billions of microscopic circuits from overloading. Engineers solved this by throwing away the crimped pipe entirely. Instead, they built a tiny holding chamber with a bucket inside, sitting exactly between two mechanical doors. In our electrical world, this bucket is called a capacitor. It's a very simple component designed to catch and hold a highly specific, very tiny amount of electrical charge. The two doors on either side are electrical switches. They are the strict gatekeepers that decide exactly when that charge is allowed to enter or exit the bucket. Here is how they work together in a strict cycle. The inlet door opens first. Electricity rushes in, perfectly filling the small capacitor, but it stops right there because the outlet door is locked shut. Then the inlet door snaps closed. Only after it's fully sealed does the outlet door swing open, allowing the bucket to dump its precise, limited payload further down the line. If you watch this happen slowly, it doesn't look very useful. It just looks like a choppy, segmented splashing of energy. It certainly isn't the smooth, restricted flow we originally wanted. The system relies on one more piece, a precise electronic clock. It acts like a metronome, giving those mechanical doors a relentless, exact rhythm to follow, and the tempo of that clock is incredibly fast. Inside a modern microchip, this rigid cycle of opening, filling, closing, and dumping happens millions of times every single second. When you run the bucket brigade fast enough, a brilliant illusion takes over. Those millions of tiny, choppy bucket dumps blur completely together. To the rest of the circuit, it looks and acts exactly like a smooth, perfectly restricted trickle of electricity. Engineers bypassed the miniaturization problem completely. They built a virtual resistor out of thin air, using nothing but tiny capacitors and razor-sharp timing. This schematic shows what those mechanical doors look like when they are etched into a chip. Instead of physical gates, engineers use microscopic switches called transistors to rapidly flip back and forth, allowing electricity through or stopping it instantly. And this diagram illustrates the complete bucket brigade in action. You can see the alternating switches acting as the two doors, constantly shuttling charge into the central capacitor, replacing the need for a solid physical resistor. Replacing bulky physical parts with this clever timing logic is what allows us to squeeze so much power into such small spaces. We carry the results of that clever trick with us everywhere we go. If chip makers were still forced to use traditional, bulky resistors to process the audio and video in your smartphone, the device would be the size of a brick, its battery would die in minutes, and it would constantly overheat in your hands. Every time you stream a song, scroll through photos, or record a video, you are relying on billions of tiny, invisible bucket brigades, working furiously in the background to keep the digital world flowing exactly as it should.